In this lesson, we are going to look at solving systems of linear equations. The solution of a linear system can be estimated by graphing both equations on the same grid. If the two lines intersect, the coordinates xy of the point of intersection are the solution of the linear system. So it's when you're graphing the two lines, wherever they intersect, that is called your solution. So each equation of the following linear system is graphed on a grid. So we've graphed the two lines, the 3x plus 2y equals negative 12, and we've graphed the negative 2x plus y equals 1. These intersect, and they intersect at this point. So this point here is at the x coordinate of negative 2 and the y coordinate of negative 3. This is called the solution of the linear system. So we actually just looked at that. The point of intersection is at negative 2, negative 3, and that is called the solution of this system. We can verify the solution. So what we do is we check that the coordinates negative 2, negative 3 satisfy both equations. So you take the first equation, the 3x plus 2y equals negative 12. And notice, remember our coordinates were negative 2, negative 3. So we replace the x value with negative 2 and the y value with negative 3. And we check to see that the left-hand side equals the right-hand side. We then need to repeat the process with the second equation because it might satisfy one equation but not both. And therefore, it's not a solution. In order for it to be a solution of the system, it must work in both equations. So we replace the x with negative 2 and the y with negative 3, and we want to make sure that the left side equals the right side. And in this case, it does, and it should, because it was the intersection point of the system. So what we need to do, if we want to solve this linear system, we need to graph it. Now, there are some strategies we did for graphing in a previous outcome. One was we used table of values. The other one was we used slope-intercept form. And the third one was we found the x and the y intercepts. Any of those will work for this type of problem. So it's kind of up to you on what you want to use. In this example, I will use the slope-intercept method just to refresh your memory on that one. So what we do, we take the equation and we want to rewrite it as y equals mx plus b. So we need to subtract x from both sides. So we have negative x plus 8. So what this tells us that our y-intercept is at positive 8, and our slope is negative 1 over 1. Now we need to do the same thing with the second equation. And it's a good idea to look at both before we graph so that we know how high up or how low our intercepts go, so we know how to scale our graph. Y by itself. So we're going to have minus 2y equals minus 3x plus 14. And then we're going to divide everything by minus 2. So we end up with 3 over 2x minus, so this is our y-intercept, and our slope is 3 over 2. So what we know is we have a y-intercept of positive 8 and a y-intercept of negative 7. So pretty much we can split this in half. All right, so we'll draw our axes. There's our xy axes. And if we start with the first one, y equals negative x plus 8. Graphing using the slope-intercept method means we start at the y-intercept. So we go up 8, and we put our first point. Our slope is negative 1 over 1. So from 8, that means we go down 1 over 1. down 1, over 1. And we repeat this process. Good idea to be as accurate as possible, so repeat your slope a number of times, because one thing about the graphing method is we want to take away any sort of estimation or approximation that we absolutely can. So now we take the next one. We start down at -7. And this time we are going up 3 and over 2, and we're going to repeat this process. And in this one, and my graph is off a little bit, I'm unorientated, but we would have intersected at this point right here. So let's find out what that is. It's at where x is 6 and y is 2. So the solution of this region is 6, 2. And it's very important that you don't just graph it and leave it, that you actually indicate what your intersection point is. So it's 6, 2. On this next example here, we've got one plane leaving Regina at noon, traveling 1,400 miles to Ottawa at an average speed of 400 miles per hour. Another plane is leaving Ottawa at the same time to travel to Regina at an average speed of 350 miles per hour. So the linear system that models this situation is the distance is equal to 1,400 minus 400t, and the distance is equal to 350t. The distance is miles from Ottawa, and t is time in hours since the plane took off. We want to graph this linear system. Again, we can use slope-intercept form, or we could find the intercepts of each. What we do know is that our axes are going to be dealing with the positives, because it's all time and distance. We've got our time on the x and our distance on the y. In that first equation, d equals 1,400 minus 400t. Make sure you recognize this is your y-intercept. Remember, your slope is always the value that is with the variable. So the slope is negative 400 over 1. In the second equation, what is your y-intercept? It's 0. This is the same as saying plus 0. So 0 is your y-intercept, and our slope is 350 over 1. Now, if we are going to use slope-intercept method, recognize we are not counting 350 units. We have to look at the scales. Now, we need to make sure we can go to 1,400, and I believe we can go up by 100s here. So 100, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13. Here's 1,400. All right, this would be 1,200. 1,000, 800, 600, 400, 200. All right, so we're at 1,400. We're going down 400 and we're moving over 1. Now, if we want to space out this time, we can actually put every second one to represent 1 hour. So we're going to go down 400. 1,400 subtract 400 is 1,000. Now we need to go over 1 hour. So we need to go on our grid, we are going over 2. Go down another 400. 1,000 subtract 400 would be 600. Go over another 1, we'd be at 2. 600 subtract 400 would be 200. Go over another hour, we would be at 1. Now we can make our line. Second one, we're starting at a y-intercept of 0. We're going up 350 and then over 1. Now 350 plus 350 would be 700. So we go up 700 and over 1. Now we have an intersection. We are intersecting, it looks like, at approximately 2 hours and 700 kilometers. Now I say approximately, or I guess it would be 700 miles, because we don't know exactly. That is the downside of graphing, is that unless you are using technology and you can get an exact intersection point, your graph is only as good as your pen, your pencil, and a ruler if you use it. And if they happen to intersect on whole numbers, you may luck out and get the exact value. If they do not intersect on whole numbers, it is very hard to get the exact value. You will probably end up approximating. So when do the planes pass each other and how far are they from Ottawa? Well, it seems that they pass each other after 2 hours and that they would have been 700 miles from Ottawa. All right, last example. To visit the Head Smash and Buffalo Jump Interpretive Center near Fort Macleod, Alberta, the admission fee is $5 for a student and $9 for an adult. In 1 hour, 32 people entered the center and a total of $180 in admission fees was collected. So the first thing we want to do is write a linear system. Now remember, this is a higher level type of question. To get that linear system, especially on an exam, if you don't know what it is, ask. All right, you won't be a level 4 because the level 4 means that you could actually determine the linear system, but you will still be able to solve it. What we do have is we're dealing with admissions for students and adults. So let's let S represent the number of students, and we'll let A represent the number of adults. Now what we do know is that in 1 hour, 32 people entered the center. So however many students and however many adults, there are a total of 32 people. The next thing we know is that for each student, they got $5, and for each adult, they took in $9, and they took in a total of $180. So there is your linear system. So I'm just going to rewrite those. And now what we want to do is we want to graph this linear system to find out how many students and how many adults actually visited during this time. Now again, you could choose to use slope-intercept, or we could find the x and y intercepts of each of these. It is up to you. Maybe in this case, because we've done 2 questions now where we've used slope-intercept, let me just refresh your memory on how it would work if you were finding the intercepts to graph. So if we wanted to do S plus A equals 32, and we want to find the S-intercept, you let A equal 0. All right, you always let the opposite value be 0. So what we have is S plus 0 equals 32, so S equals 32. Now if we want to find the A-intercept, you let S equal 0. So we'll have 0 plus A equals 32, so A equals 32. So in this case, both intercepts were 32. All right, let's look at the second. We want to find the S-intercept. So we're going to let A equal 0. So we're going to have 5S plus 9 times 0 equals 180, which is going to give us 5S equals 180. Divide by 5, and you get S equals 36. Now we want to find the a-intercept, so we let s equal 0. 5 times 0 plus 9a equals 180. So we'll have 9a equals 180. Divide by 9, and you will have a equals 20. So all of our intercepts are positive, which should make sense. We are dealing with numbers of people. Now in this case, it doesn't matter which axes you make the S and which you make the A. So we'll pick one. Now on the S's, we have an intercept of 32 and an intercept of 36. So we need to see what kind of scale we could use. Both of those are divisible by 4s, so maybe we could use 4s. So we got 4, 8, 12, 16, 20, 24, 28, 32, 36. In the A's, we have a 32 and a 20. Again, both are divisible by 4s. We probably could have spaced it out even a little bit more, but this will work. So now what you do is you graph the intercepts of each one. So S is 32, A is 32. So at 32 and 32, we put our points, and then we join those lines, or those points together. 36 and 20. When S is 36 and A is 20, we join, and now we have an intersection point. Now remember, we're talking about people. We are going to make estimation because it didn't fall on an intersection of the grid. What we do have here is 28 students. And remember, there was a total of 32. So our estimation now should be fairly accurate because we would have to have 4. Even though it didn't fall on the grid, we can say, okay, something in our graph was a little bit off. Maybe we didn't use a ruler, which I didn't. And therefore, it's off a little bit. So it's around 28 students and 4 adults. But maybe it was 27 and 5 or something like that. So this is an approximation, okay, from our graph. And that is how you solve systems using graphing. Graphing is a nice visual, but unless you are using technology, it is only an approximation.